Hello, everybody. Let's start our joint session of European Non-Associative Algebra Seminar and Operator Algebras and their application. Today, our speaker is Professor Topley, University of Bath, United Kingdom. And the title of the talk is Modular Representation Theory and Finite W-algebras. Please.
Yeah, hello. So thank you very much for inviting me to give this talk. It's very nice to have an opportunity to introduce myself to you and to tell you about some of my research. I think this might be the first time that I'm giving a talk in front of a lot of you, so I wanted to give a survey of some of the work that I've done over the last sort of 6 or 7 years. So some of the content is actually not to do with finite W-algebras at all. I think the first half is just about restricted representations of Lie algebras. So I think I sort of changed the subject so that it might be sort of most appealing to the audience here. So I hope this goes well. The first part will be very slow, so I hope you'll excuse me if you're an expert in modular Lie algebras, but I'm going to start with the definition of a Lie algebra. So we're going to work over a field K, and all vector spaces will be defined over K. And the most important Lie algebra to understand is the general linear Lie algebra. So this is just endomorphisms of your vector space, and the multiplication is given by the commutator. So this is the Lie bracket here. That's the commutator on GLV. So Lie algebras, you can define them to be just the subalgebras of GLV as we vary V over all vector spaces. Or equivalently, we can take a vector space which has an alternating bilinear multiplication satisfying Jacobi. That's the textbook definition. And a representation will be a homomorphism from this chosen Lie algebra into some GLV. We say that V is a G module in case that we have a representation. So the first example of representation is the adjoint representation. This is the sort of left regular representation of your algebra, where you just multiply on the left by x. Simple modules are the ones that have no submodules between other than 0 and v, and the goal is to classify all simple modules. You could say that this is perhaps the ambition of any pursuit in representation theory. So the universal enveloping algebra is just the quotient of this free associative algebra, Tg. That's the tensor algebra on G by this ideal here, which depends on the Lie algebra structure. So the tensor algebra just has a basis consisting of words in some basis for your Lie algebra G, and the multiplication is just given by concatenation. So one of the first important theorems about enveloping algebras is the PBW theorem. And a simplified version of this says that the enveloping algebra is isomorphic as a vector space to the algebra of polynomials on G star. So here we're identifying the Lie algebra G with the linear functions on G star. And so the free polynomial algebra generated by G is this KG star. And it's easy to see that a basis for this polynomial algebra is a spanning set for your enveloping algebra, because certainly if you want to take some unordered monomial in a basis for G, and then you want to rewrite it in ordered fashion, then you can do so by commuting things past each other using this relation here. And the only cost you have of using this relation is to pick up extra terms of lower degree. So these lie in degree 2 and these lie in degree 1 inside the natural grading on Tg. And so a simple inductive argument says that ordered monomials span your enveloping algebra. And the hard part of the PBW theorem is proving that they are indeed a basis. So take A to be an associative algebra, and I'm going to define some slightly non-standard notation, which is that Lie of A is the Lie algebra built out of A just by taking the Lie bracket. So the Lie bracket is the commutator. And an example of this would be if we take A to be the endomorphisms of a vector space, then Lie A is just the general linear algebra on that vector space. So here is an incredibly important statement, which is an adjunction between the enveloping algebra functor from Lie algebras to Sorry, was I muted then? No, I was just asked to unmute. So the opposite functor, which goes from associative algebras to Lie algebra, is Lie A. Okay, and the way that we prove this adjunct is very simple. I can explain it right now. So if we look at the definition of the enveloping algebra again, so what is an algebra homomorphism from UG into some choice of associative algebra A? Well, we just have to take a linear map from G into the associative algebra A. This will define by the freeness of this algebra here a homomorphism from TG into A. But if we want it to factor through the quotient, then we need for the Lie brackets to be sent to the commutators in A. And likewise, if you want a representation of a Lie algebra, then you need a linear map from G into A such that the Lie brackets go to the commutators. Okay, so this kind of gives you a clear explanation of how this adjunction works. But if we take the special case of where A is the endomorphism of a vector space, then we'll see that the representations of G are the same as the representations of UG. Okay, so if we want to study reps of G, then it suffices to study reps of this large associative algebra here. So now let's take K to be characteristic P. For instance, we might take the algebraic closure of the finite field with P elements. We say that G is restricted if it emits a P mapping, and I denoted X goes to X to the P. This is a map from the Lie algebra to itself. And its defining property is that this associated map psi, which goes from G to UG by the expression X goes to X to the P minus X to the restricted structure on P. So this is the Pth power in the enveloping algebra. This should satisfy two conditions. So the first is that psi is P semilinear. That means that it's additive, but also that it's sort of almost linear with respect to the scalars. You just pick up a little twist by the Frobenius, and this should be hold for all x, y, and lambda. The second property is that psi of G should lie in the center of UG. And just to give one example of a P semilinear map on an algebra, or just from a vector space to a vector space, take a commutative algebra, then the map that takes Pth powers, the Frobenius map on this algebra is P semilinear. And this psi is supposed to be emulating exactly this structure. So we've got a sort of non-commutative version of the map on the coordinate ring of G star, which takes Pth powers. So how can we construct restricted Lie algebras? Well, here is the fundamental example that gives you basically all known classes of examples of restricted Lie algebras as far as I'm aware, apart from maybe taking the free restricted Lie algebra and taking its quotients. But that's kind of cheating, isn't it? So if you take an associative algebra and then you take some Lie subalgebra which is closed under the Pth power map, so that means we have closed under the bracket, closed under, this is denoting taking Pth powers in the associative algebra A, then G is a restricted Lie algebra. And I can explain why this is true very quickly. So if we take an element in this, in which we view as the algebra, define two linear maps from A to A. The first is left multiplication by X, the second is right multiplication by X, and the third is the difference between the two, which we'll denote add for obvious reasons. Now, because A is associative, we know that left multiplication by X and right multiplication by X. And so we can use binomial calculation. We consider add X. This is an endomorphism from A to A, just a linear map. Its Pth power is also, well, it's not a linear map anymore, but it's certainly a map from A to A. And this is equal to this expression here by the definition above. And because of binomial theorem and the vanishing of binomial coefficients in positive characteristic, we learn that it's equal to this expression. But left multiplication by X on an associative algebra P times is just left multiplication by the Pth power in that associative algebra, and similar for right. So we obtain this equality here. Now we can do this calculation in the enveloping algebra of Lie A. And this time we replace this X to the P here by X to the P in the enveloping algebra. And we learn that add X P times is equal to add X to the P. This is X to the P in the enveloping algebra. So now taking the difference between these two equalities, we know that add x to the p in the enveloping algebra is equal to add x to the p in the associative algebra. And so psi of x is equal to x to the p minus x to the square brackets p is an element of the center of the enveloping algebra. Okay, so we've proven one of the properties that was required of psi. The second property is actually proven by some formulas of Jacobson, which I'm not going to write down, but they're rather amazing. If you take any associative algebra in characteristic P, and you want to know what's the difference between taking x plus y to the P or x to the P plus y to the P, then this can actually be expressed in terms of a huge summation of commutators. And Jacobson wrote this down very precisely. It's very beautiful. And this is how you would prove P semilinearity of this particular map here. So now we can generate some more examples. We take A to be associative and we take G to be a Lie subalgebra stable. And I've just shown you that you get a restricted structure on G. So let's take an example of GLN. Well, this is just endomorphisms of a vector space. This is definitely closed under its p powers. So this is a restricted Lie algebra. Now let's take A associative again. We take the derivations of A. Then this is stable under its p-th powers. So, I mean, if you take a p-th power in characteristic P, then we know that we get another derivation. And so we have that der A as a restricted Lie algebra. Now let's take G to be an algebraic group. Then the Lie algebra is defined to be a subalgebra of the derivations of the coordinate ring on G. And it's in particular, it's some derivations which commute with the derivations which commute with certain automorphisms coming from the group action. And so because if you take a derivation which commutes with a certain collection of automorphisms, then the p-th power also commutes with those automorphisms. It follows that the Lie algebra of G is also closed under the p-power mapping, and therefore it is a restricted Lie algebra as a natural restricted structure coming from this group. So now I can tell you what you can do with the restricted structure. What does it give you in terms of representation theory? So the main difference, and this is the kind of the huge difference between working in characteristic 0 and characteristic P when studying reps of Lie algebras, is that you have this P center. So this is just the subalgebra of your enveloping algebra, which is generated by the image of the map psi. And let me give you a definition before I state the lemma. So the Frobenius twist of an affine algebraic variety is just defined to be x upper 1, which is the maximal spectrum of p-th powers. So that's quite a sort of naive way of writing it down, but it's suitable for our purposes. So the lemma says that the p-th powers, sorry, the p center is isomorphic to the p-th powers in the coordinate ring of G star. And this in turn is, by definition, the coordinate ring on the Frobenius twist. So this basically follows from the PBW theorem. The P center is sort of, almost the same as p-th powers modulo lower terms. The enveloping algebra is the same as kg star modulo lower terms. And so that's where this identification comes from. Well, one way of saying it anyway. The second is that UG is a free ZPG module of rank P to the dim G. And again, this comes from the PBW theorem. So let's think about the commutative analog. So we take the coordinate ring on G star. This is just a polynomial ring generated by dim G elements. And if you have a polynomial ring generated by n elements, then it is a free module of rank P to the n over its p-th powers. So this is how you obtained this statement here. So we can now define reduced enveloping algebras. So let G be finite dimensional. We have an identification between the Frobenius twist of G star and the maximal spectrum of the P center. So there's an identification of sets of G star with its Frobenius twist. And if you haven't seen that before, then you can just blur your eyes slightly and imagine that the one isn't there. But we can make this very explicit. So if you give me a linear function on the Lie algebra, then I can give you a maximal ideal, and is the one which is generated by psi x minus chi x to the p. and this is where where X is in G. And the reason that this does give you a well-defined maximal ideal and not the entire algebra is because psi is P semilinear and chi to the P is also P semilinear. Okay, so we've got a classification of maximal ideals now in terms of the dual space of G. And the reduced enveloping algebra for chi is defined to be this quotient by this ideal generated by the chi maximal ideal. And the restricted enveloping algebra is just the one corresponding to the 0p character. So we've got a few more lemmas here. So the dimension of U chi G is P is the dim G, and this just follows from the statement about UG being a free module of that rank. Every simple module is a U chi G module for some chi. This is essentially Schur's lemma, because these algebras UG are not finite dimensional. You have to use something, a slight upgrade of Schur's lemma, so something like Dixmuir's lemma or Quillen's lemma. And we say that V has P character chi if it belongs to U chi G. The final statement is that every representation of G is finite dimensional. So if you take an algebra of dimension D, finite dimension D, then the maximal possible dimension that a simple module could have is the square root of D, and that occurs precisely when you have a matrix algebra of rank square root D, and its dimension is D. So we can say that irreducible reps are bounded above by P to the half dim G. So the Katz-Weisweiler conjectures inside. In fact, this slide says first, but this slide I'm really introducing the fact that there are two. So in this very important paper, 1971, Katz and Weisweiler made these conjectures about restricted Lie algebras, KW1 and KW2. And quite a lot of my research has revolved around these two conjectures or ideas that sort of come off it. So if we write mg for the maximal dimension of simple modules, then the KW1 says that provided G is restricted, the maximal dimension is given by this very neat formula, P to the half dim G minus ind G. That's the index of the Lie algebra, which was introduced by Dixmuir. And it's just defined to be the minimal dimension of coadjoint stabilizers. So I told you what the adjoint representation is. And because G acts on its on the space G, it also acts on the dual space G star. And the stabilizer here is just defined to be the elements in G which annihilate chi under this coadjoint representation. Okay, so this is quite striking. I mean, first of all, because it's a very simple formula to write down, and it's incredibly general, but it's also very reminiscent of the work of Kirillov and Constant on the orbit method. So Kirillov showed that representations of nilpotent Lie groups are really controlled by the dual space of the Lie algebra in a very precise way. So the coadjoint orbits classify the unitary representations. And so the fact that G star is getting involved in this kind of very precise way in these kind of global invariants of the category of modules is certainly reminiscent of that. And this statement belongs to the kind of orbit method philosophy. So I was playing around in 2016 trying to work out whether it was possible to prove or disprove the first Katz-Weisweiler conjecture for Lie algebras which are not restricted. Certainly the statement itself, if you look at it, if you look at this statement here, it doesn't require for your Lie algebra to be restricted at all. So you could hope that it holds in a more general setting. But I found counterexamples. I want to explain how. So there was a little algebraic trick, which I think I can describe easily. So let's take any Lie algebra G, finite dimensional, not necessarily restricted. Then we can define the P closure of add G, which is just taking add G and then taking all the iterates of taking Pth powers. So add G lives inside the endomorphisms of G. And we can just take Pth powers over and over again. And what we get turns out to be a vector space. It is in fact a Lie algebra. It's the smallest Lie algebra, which is restricted and contains add G, is the P closure. Now, if we take any two elements in this P closure, D1, D2, they're derivations of G. We can form the semi-direct products, just D1 appended onto G, D2 appended onto G, and it turns out that their enveloping algebras are isomorphic. I can write down very simple isomorphism. So there it goes via an intermediate step. So let's take D0 to be the zero derivation. And for D1, we can write it as a sum of add xj to the pj for certain elements xi. And now I define the isomorphism just to be the map which sends G to G, but it sends D1 to the element D0 plus the sum of these xj p to the j's. And it's very, very easy to see that this expression on the right, D0 plus the sum, is going to commute with G in exactly the same way that D1 does. That's almost by definition. But because G together with this expression on the right give you a generating set of the enveloping algebra, it follows that this must be an isomorphism. Now this is related to quite an interesting algebraic problem called the isomorphism problem for Lie algebras. You can ask whether the enveloping algebra uniquely determines your Lie algebra up to isomorphism. This is a problem which I learned by reading the papers of Hamid Yousseifi, who gave a talk in an earlier session of this seminar series. It's a Fox type problem. And well, there are no known counterexamples to this sort of question if you work in characteristic 0. In characteristic P, there are obviously counterexamples in the non-restricted case. In the restricted case, you certainly can't obtain counterexamples using this statement here because the P closure of add G is just add G. And if you take two inner derivations and you form these semi-direct products, then it's just a split central extension of G. So you really don't learn anything new there. It's quite interesting that this method finds obstructions precisely at the restricted case. I would expect that the isomorphism question has a positive answer, i.e. the enveloping algebra does determine the Lie algebra in the restricted case. But it seems to be a very hard problem indeed at the moment. In any case, I took some non-restricted Lie algebras and I was able to exhibit examples using this method where two Lie algebras had isomorphic enveloping algebras but different indices. And of course, the maximal dimension of simple modules is definitely determined by the isomorphism class of the enveloping algebra. So if the KW1 was going to hold for these Lie algebras, then you would need for the indices to be the same. So it's a slightly roundabout method. Now I'll talk about a positive result towards this conjecture. So if you take G to be a restricted Lie algebra with a characteristic much larger than n, then it turns out that the KW1 does hold for G. So this is, I suppose, a very strong positive result. I have to say that the proof was much easier than it might seem. So what we do is we say that S is a solvable weak polarization of chi and G star. If S is a solvable Lie algebra satisfying this property here, this means precisely that chi gives a one-dimensional representation of S, and S should have dimension half dim G minus int G. So the notion of a polarization was introduced by Kirillov in his thesis when he was developing the orbit method. And a polarization means exactly that you have a solvable Lie algebra satisfying this property, but this number here, the index, should be replaced by the dimension of the stabilizer of chi, the centralizer of chi. And of course, the dimension of the centralizer of chi is larger than the index in general. So this is a kind of weaker condition that we're placing on the solvable algebras. But this was sufficient for our purposes, so we call them solvable weak polarizations. And these things were actually known to exist in characteristic 0 for quite a long time. So it even appears in Dismir's book on enveloping algebras. And so we use the Lefschetz principle from model theory to show that every chi and G star admits a restricted weak solvable polarization. The Lefschetz principle, I mean, sometimes the expression is used in kind of quite vague terms, but there is a very precise expression of it in model theory, which comes from the completeness of theories of algebraically closed fields of a fixed characteristic in the language of rings. And so basically the idea is that if you can write down the statement that you want to verify in the language of rings, so it has to be a sort of a finite sentence. So in our particular case, the sentence was, for a Lie algebra G of dimension n, and for any chi and G star, there exists a solvable weak polarization for chi. So this is something that you can write down in the language of rings. And because it holds over the complex numbers, it means that it holds in positive characteristics for sufficiently large n. Okay, so this was how we obtained it in large characteristics, and then finally use some fairly standard tricks in sort of modular reps of Lie algebras. So once you have a solvable Lie algebra satisfying these properties, you can show that every simple module is a quotient of a module induced from a one-dimensional UKS module. And these quotients, these induced modules have precisely the dimension which is predicted by the KW1 bound, and so their quotients do as well. Well, the quotients are bounded by that dimension. Okay, so this was how we obtained this result. And now I'm going to move towards finite W-algebras. So I'll talk about reductive groups to start with. So let's take a reductive algebraic group. Here are some examples. A torus is a reductive group, has a abelian Lie algebra. The general linear group is the sort of prototypical reductive group. The special linear group has determinant 1 and trace 0 matrices as its Lie algebra. And then you have these are examples of the classical groups. These are the classical matrix groups and the exceptional groups, EFG. And actually up to every single reductive group can be obtained by taking a product of one of these examples or some of these examples and then factoring out by a finite central group. So these are the ones to bear in mind. And we're going to assume that P is not too small. And I won't say precisely what that means, but I'll just illustrate why it's necessary with a cautionary example, which is SL2 and positive characteristic 2. So here SL2 follows directly from the relations that you have a central element H, and so your Lie algebra is a nilpotent Heisenberg. So we want to avoid those kind of things. The hypotheses that we place here are specifically designed so that the Lie algebras we obtain are those which we recognize from characteristic 0, and they should have a sort of homogeneous representation theory, which we can hope to describe in uniform terms. So the second Katz-Weisweiler conjecture, it says that if you have a Lie algebra of a reductive group, and you take d chi to be half the dimension of the coadjoint orbit, then all U chi G modules have dimension divisible by P. So this is another expression of the orbit method. And this was proven by Premet in 1997. So this was the first proof he gave. I should mention that there's some hope that this conjecture could hold for the Lie algebras of algebraic groups in positive characteristic under some fairly mild hypotheses, such as having smooth stabilizers. So I think that's a very interesting extension to this conjecture. In fact, it was stated precisely by Katz in a review he wrote in a MathSciNet article for Premet's proof in 1997. So, it really is an interesting idea to gun for. So let me explain in quite a crowded slide how you can reduce to nilpotent characters. So because we've taken P not too small, this one consequence is that there exists a non-degenerate invariant form on G. So if you know the background of complex semisimple algebras, then the killing form would be very reminiscent. The killing form is not always non-degenerate on reductive Lie algebras. Those are reductive groups because you can have the center, but nonetheless, you can construct one of these G invariant forms. So such a form gives rise to a G invariant isomorphism between the adjoint and coadjoint representations of the group G, or the Lie algebra G. And so we use this to define nilpotent elements of G star. So we take nilpotent elements of G, and these, unlike in characteristic 0, these can actually be described intrinsically using the restricted structure. So a nilpotent element is one which is annihilated by the sort of iteration of the P power map. So if you keep on taking x to the p and then x to the p squared. If eventually you kill it, then that is a nilpotent element. And we say that an element of the dual space is nilpotent if it lies in the image of this, applying this isomorphism to the nilpotent cone of your Lie algebra. And so Friedlander and Partial proved in 1980 that the representation theory of these reduced enveloping algebras can be reduced to the case where chi is nilpotent. And in fact, this reduction is compatible with the KW2 bound. I won't say anything more about that except parabolic induction is the key word. A result of Richardson from 1967 says that there are only finitely many nilpotent orbits on this null cone here. And I mean, of course, for the general linear group, this is just the theory of Jordan normal form. And Richardson's proof sort of leveraged this. He said that if you have a Lie subalgebra of GLN such that the image of your representation splits, so you need a complement to the image of the representation as a G module, then finitely many orbits in G implies finitely many orbits in GLN implies finitely many orbits for G. Okay. So the property descends to all the Lie algebras that we're interested in. You can take the orthogonal complement of the image of G with respect to this form to satisfy the property I just stated. And whenever you have the Lie algebra of any algebraic group, okay, I'm covering up the actual isomorphism I need. The reduced enveloping algebras for chi and G applied to chi by the coadjoint representation, these are isomorphic. And so this is saying that as we vary chi over a coadjoint orbit, we get isomorphic reduced enveloping algebras. There are only finitely many nilpotent orbits on this on the null cone of G star. And so we've taken the problem of studying simple modules for G, we've passed it to simple modules for UG, and then we've reduced that to simple modules for these reduced enveloping algebras. And now finally, we're left with a finite set of reduced enveloping algebras, which we need to study in order to understand all the representations of G. Okay, so not far off the complete solution. So Premet's theorem, this was a refinement of his proof in 2002. So 5 years after his first proof, the KW1, it says that the reduced enveloping algebra is actually a matrix algebra over this rather interesting smaller algebra UPGE, which is known as the restricted finite W-algebra. And that's going to be the subject of the rest of this talk. So we felt that U chi G was perhaps the fundamental unit of currency in studying G modules, but there is this smaller thing which perhaps could give us more information if we understand it well. The problem is that the definition of this restricted finite W algebra is hard to use. So it's given in terms of some invariants or some the endomorphisms of a certain projective module, which is constructed by induction. So algebraically, we still don't know that much about them, but there are many very impressive results. So first of all, we take an associated co-character for this nilpotent element. Okay, so let me explain what that is. In characteristic 0, there's a theorem of Jacobson-Morozov, which says that if you take a nilpotent element in your Lie algebra, then it's possible to find a triple of elements, E, H, F, inside your Lie algebra, such that E is your chosen nilpotent element, and EHFs, they span a subalgebra isomorphic to SL2. So again, in characteristic 0, this element H is a semisimple element, which gives you an integer grading of your Lie algebra. And this is what we want to get our hands on. Now, if we try to do the same in positive characteristic, then things break down quite quickly. So SL2 triples, they behave in the same way under some slightly more restrictive hypotheses, so P bigger than the Coxeter number. So they really do correspond to nilpotent orbits. But the problem is that when you take this semisimple element H, add H is going to give you a grading by the prime field, which is not what we want. So we need an integer grading. But there is a replacement for this add H in characteristic P, which is a co-character of your group. So this is just a homomorphism of algebraic groups from K star into G. And it really plays the role of add H as is done in characteristic 0. So if you look at representations of K star on a finite dimensional vector space, they're diagonalizable. So an element T can be put in diagonal form, and on a given eigenspace, T is going to act by T to the I for some integer I. So this integer grading comes from the eigenspaces of your associated co-character, and it really is the set. You should think of it as being the same grading as what you see in characteristic 0. So sorry if that's a little bit technical, but you take your grading by these eigenspaces, and well, because the grading behaves like it does in characteristic 0, we know that the semisimple element H acts on E by 2, and so E does live in the 2 eigenspace for this co-character. And for simplicity in what comes after, I want to assume that GI is odd for odd I. It gets a little bit more technical if I don't. So we take M to be the sum of all eigenspaces less than 0. This is a nilpotently algebra, and it also has the property that chi vanishes on the derived subalgebra of M. So the way to see this is that, well, E lives in degree 2, and that means that chi is supported on degree -2. Now, because we've assumed this hypothesis here, it means that M lives in degree 2 or less, and its derived subalgebra lives in degree 4 or less. So chi vanishes. It's only supported on degree 2. And so chi gives a one-dimensional representation of this nilpotently algebra. And so we finally make the definition that M chi is this sort of, we just skew chi by, sorry, we skew M by this character chi. And this is actually a Lie subalgebra of UG. And then we can define this induced module Q, QP. This is known as the generalized Gelfand-Grave module. It's just the one that's induced from this one-dimensional representation, or equivalently, it can be expressed as a quotient by a left ideal. And now UPGE is defined to be the endomorphisms of QP, but opposite. So let me just say a word about this opposite here. We're taking endomorphisms to act on the left of modules. So the multiplicative structure comes from left action, but this algebra is actually acting on the right, for reasons that will become apparent in a moment. And so because we have a right action, it has the opposite multiplicative structure. So now, how does the proof work? Well, using the theory of support varieties, you can show that this restricted module is a projective UKG module for E simple. Okay, so by the way, the projectivity, the real key here, and the reason that this definition works, this definition of M, is because M lies in degree less than 0, and the centralizer lies in degree greater than or equal to 0. So that follows from the properties of the associated co-character. So that the fact these two things don't intersect and that we're inducing up from M, this is what tells us that QP is projective. Now, if we take any simple module, then you can show that taking this many copies of your restricted Gelfand-Grave module, the HOMs into the simple module are going to have the same dimension as the HOMs from the left regular module into your simple module. So this uses Frobenius reciprocity and this fact here, which again follows from the theory of support varieties. So now, because projective modules are determined uniquely up to isomorphism by the number of times that you, by the number of copies of a projective cover of a given simple, i.e. these dimensions, it follows that actually UKG, the left module here, is isomorphic to this many copies of the Gelfand-Grave. And now I can give a fairly short argument to explain why this isomorphism holds. If you take any associative algebra, then the endomorphisms of it as a left module, they are precisely the algebra acting on itself on the right. So that tells us that the algebra is isomorphic to the endomorphism, the opposite endomorphism ring of its left regular module. And now we've got the isomorphism between UKG and this thing here. And because we're taking endomorphisms of certain number of copies of a module, we see that this is just matrices over this restricted finite W algebra. Okay, So this gives a very strong proof that, or a very sort of clear proof that the KW2 bound holds, because modules over this matrix algebra are obtained by taking modules for this smaller algebra and just putting it into a column vector. So certainly we have this dimension property. So what happened next was mostly in characteristic 0. So in this same paper in 2002, Premet lifted this finite dimensional modular algebra into the complex numbers, and he showed that this complex version of it here admits a filtration such that the associated graded is naturally identified with the coordinate ring on the Sloterdijk slice. So I'll talk in a moment about what this slice is. And Gannon-Ginsberg saw this relationship between the Sloterdijk slice and this filtered algebra, and they knew straight away that there was a quantum Hamiltonian reduction story going on here. So I'll probably say a few words about that as well in a moment. And so they obtained some of his results from the characteristic 0 setting in a very succinct way. It's a very nice short paper of about 10 pages, I think. Losif introduced in 2010 the theory of deformation quantization, and he really kind of came in with a bang. He proved some very, very impressive theorems about these W-algebras and the way that their representations relate to those of the enveloping algebras of complex semi-simple algebras. So especially the theory of completely prime primitive ideals. This was something that had been studied, seriously by Joseph and many others back in the 1980s, but the sort of some of the hardest problems had kind of come to a standstill, but things picked up again quite quickly when Losif's machinery came into the picture, and Premet was going back and forth feeding information to him, and he'd feed information back to Losif. And finally, in 2019, we sort of took a lot of these developments that had happened in the complex setting, and we reset them in positive characteristic. So we're sort of building analogs of some of those complex results, but in characteristic P. And Premet had reduced these complex algebras into positive characteristic and got lots of traction on that in the interim years. But because he was reducing a fairly unknown algebra into positive characteristic, in particular, the structure constants were not known, it meant that there were sort of unknown bounds on which positive characteristic this algebra could live in. But we went back and built up a sort of foundation which works under these very mild assumptions, which I mentioned earlier. So P is not too small. These are, in particular, if you know about the rep theory of these the algebras, then I'm assuming the standard hypotheses which appear in Janssen's notes. So let's refresh the notation again. So we've got the algebra of a reductive group and a nilpotent element. We have this element associated by a non-degenerate bilinear form, or by the isomorphism attached to that. We have the associated co-character, which is something like the add H in an SL2 triple, giving a grading. We have this Lie algebra M. And although the relationship between Lie algebras and algebraic groups is certainly not kind of a nice one-to-one correspondence in positive characteristic, it certainly isn't as pretty as characteristic 0. It does so happen that this particular Lie algebra is algebraic. There's a fairly simple argument for that. So now we have to take a graded complement to the image of add E, and we define this transverse slice, which is an affine variety given by I plus the image of this complement. Okay, so this is how to best motivate it. So if you take the orbit of chi under your group, then its tangent space is GE. And so if you take the tangent space at chi of this variety, then you're going to get a complement to the orbit of V chi. So this is the sense in which it's transverse. So the tangent space of the orbit and the tangent space of the slice, they direct sum together to give you G, or G star in this case. Now there's a funny looking lemma here, which I'm going to have to use, which is that if you take the perp to M, which is just the functions vanishing, the linear functions vanishing on M, then there's an isomorphism between M cross S chi and chi plus M perp. This is just given by the adjoint, the co-adjoint representation. So this is a subvariety of G star. This is a subgroup of G. So this is going to act on this and send it into G star. In fact, it sends it isomorphically to this variety here. So in algebraic terms, what does this mean? Well, the coordinate ring of chi plus M perp, if we take the invariance, then this is isomorphic to the coordinate ring on the slice. Now, the important thing about this is that it equips this slice with a Poisson structure by the process called Hamiltonian reduction. So G star has a Poisson structure, its coordinate ring is a Poisson algebra. And if we take any two elements in this algebra here, and we lift them up into the coordinate ring of G star in an arbitrary fashion, and then take their Poisson bracket, then project back down, then, you know, in any normal situation, lifting and then multiplying and projecting would not give you something that's well defined. But it turns out that if you take the pre-image of these invariants under that projection map, then they lie in the Poisson idealizer of the kernel of the projection map. And so this is the situation of Hamiltonian reduction. This is what makes the Poisson structure here well defined. And so there is a Poisson structure on this coordinate ring of the slice, which is rather natural. So let's state the definitions of W-algebras without the word restricted. So the Gelfand-Graefe module is the this induced module, which can be expressed in the way I've written it here. It's the quotient by this left ideal. So exactly the definition I wrote before, but without the chi. So we're no longer taking reduced enveloping algebras. The finite W-algebra is just the endomorphisms which are equivariant with respect to M. This is a slightly different detail, something which doesn't crop up in characteristic 0 as well. And the extended finite W-algebra is just the opposite endomorphisms. And I'll explain in a moment why there are sort of two W-algebras knocking around all of a sudden. So another way of writing this down is that the finite W-algebra is isomorphic to the invariant ring by the group inside this module. So this is, the alarm bell should be ringing now because this shouldn't be an algebra. This is a left module and I'm taking the invariance inside it. But it turns out that just as the Poisson structure was well defined inside here by this sort of process of lifting, multiplying, projecting, the algebra structure is well defined inside here by lifting, multiplying, projecting, and it's the same calculation. The reason that these two algebras are not the same is because in positive characteristic, Lie algebra invariants are not the same as group invariants. The Lie algebra invariants in general can be bigger, as we already saw with the p-center. So the Cashdown filtration is the one, so this is defined by placing the ith graded piece in degree I plus 2, and so UG. This again has a very sensible kind of corresponding motivation inside the coordinate ring on the slice, but I won't talk about that now. But it descends to a Cashdown filtration on Q and on both of these finite W algebras. And the PBW theorem for these finite W algebras just says that the associated graded algebra is the coordinate ring on the slice. And the hard bit of the theorem, of course, is that the graded of the invariance is equal to the invariance of the graded. That requires a spectral sequence argument. And similarly, we prove this statement here. I won't say any more about that, but these are the extra invariants which are knocking around because Lie algebra invariants are not the same as group invariants. So what is the p-center of a modular finite W algebra? Well, the p-center in the enveloping algebra can be mapped down into Q. And because the image is definitely invariant under the adjoint action of M, add M, it follows that we get some central elements in U hat, GE. And the image is called the p-center. If you want to take the p-center in UGE, then you just take the group invariance. So group invariance will take you into they'll take you into Q add M. So this is an additional statement which compares the two W-algebras and describes how they interact with their p-centers, and it's analogous to one of the lemmas I wrote down earlier. So if you take any algebraic subvariety of the dual space of G, then you can take a corresponding ideal inside the p-center, because we've identified G with the maximal spectrum of ZPG, as I mentioned earlier. So we take IY to be the defining ideal, and we can define this kind of generalized reduced enveloping algebra, UYG, which is just factoring out by this central ideal. So Scriabin's equivalence is probably the last result of this particular paper. I've got quite a lot more slides, but I'll rush through. I suppose I should probably finish at 5:02, or do you want me to carry on until the hour? I'll just carry on until I'm told to stop. So we've got these isomorphisms between this particular reduction of the enveloping algebra and matrices over U hat G. So you can see this as a sort of globalization of Premet's theorem. And if you take the reduction over the slice, then you get matrices over the honest finite W algebra. And this is the one that really looks most like characteristic zero. Okay. So how can we use these results that I've described? Well, the simple modules, we know they have dimension divisible by p to the d chi. And we say that a module is small if its dimension is precisely p to the d chi. And in a survey article in 1998, Humphreys conjectured that every U chi G has a small module. So by Scriabin's equivalence, we know that they're related to one-dimensional representations of UGE. The relationship isn't quite as kind of simple as it might first seem. They're not just the same thing, because, well, how can I say it? It's essentially because the dimensions of orbits of elements of this variety are not all the same. But I'll gloss over that detail. What's true is that the existence of a one-dimensional module for this algebra is equivalent to U chi G having a small module. Okay, so really hunting for one-dimensional reps is the game in Humphreys' conjecture. So, but the one-dimensional reps of this are very hard to study because presentations are not known in general. As I say, this is just the invariance inside some module, and we sort of generally have no idea what the relations are, even though we know that it's an almost commutative filtered algebra. So we gave a proof of this in 2021 together with Premet. And so again, under the standard hypotheses, or p not too small, every reduced enveloping algebra has a small module. So the steps here were to reduce to the case where the p character has a rigid nilpotent orbit. So these are a special class of nilpotent orbits which can't be obtained by some proper Lustig-Spaltenstein induction. I won't say more about that. Now, UGE, through a huge amount of work by many authors, it was known that there was a unique one-dimensional representation in the rigid case, except for 5 orbits in exceptional algebras. So the main names in that theorem, by the way, are Premet and Losiv, and some early work by Goodwin, Roller, and Ubley. And there are these interesting exceptions in the exceptional algebras. And then we had to build a Z form for these particular rigid finite W algebras and then reduce that modulo P. So that was quite a technical process. So that was published in Advances a couple of years ago. So in the last few minutes, I'm going to try and talk about the shifted Yangian and its relationship to W algebras. So this is a Hopf algebra, and it's a filtered deformation of the truncated currents. This is a typo here, so there should be a square brackets T appearing. And it's given by these generators here. I mean, I'm only writing this down just to give you a sort of a vague idea. Looking at complicated generators and relations, it's not a useful thing in a talk, but I just want to show you how crazy these algebras are. So they have a big presentation, and they were studied by a lot of people in characteristic 0, but I made the first study in characteristic P with John Brunden, and what we did was we lifted the P center of this restricted Lie algebra. So we constructed a p-center inside this shifted Yangian, which lifts the p-center on the enveloping algebra of this particular restricted Lie algebra. And so working with Yangians involves dreaming up beautiful formulas involving sort of power series which encode the generators. So we knew that we had to lift the diagonal elements. That was the only hard bit of coming up with the formulas. And so we wrote down some expressions which were very symmetric with respect to P. And lo and behold, they did indeed give us the correct lift that we wanted. So this is how we constructed the P-center, although there was much more work than I'm suggesting. And Brundtland and Kleshchev, they defined a homomorphism from this shifted Yangian to the finite W-algebra in type A via some crazy formulas. And in fact, you can say exactly what the kernel of this homomorphism is. And the kernel is just generated by a list of elements. And so you get a precise presentation for this finite W-algebra for GLN. And so we use this to classify the small modules for GLN using this truncated shifted Yangian. So we gave a very precise description of the one-dimensional reps for this truncated shifted Yangian in positive characteristic. And they were described combinatorially by this column-connected tableau. And this gives an analog of Magellan's theorem, which classified completely prime primitive ideals of the enveloping algebra of complex GLN. And the consequence was that every small module is parabolically induced. So this is a much cleaner way of describing the representations rather than saying that they come from some Yangian. This is very classical stuff. So it brings the description down to earth a little bit, I think. And then finally, in this last piece of work, which I'll mention, this was a paper with Simon Goodwin again, published, I think, in 2021. Well, we know that the p-center of this Yangian is generated by some nice elements. We can project them down to this truncated Yangian. The ideal generated by these canonical generators is denoted like this, and we define the restricted version to be as expected, just dividing out by this ideal given by the augmentation of the p-center. And we were able to show that the Brundtland-Kleshchev homomorphism, the isomorphism, in fact, factors to an isomorphism between the restricted truncated shifted Yangian and the restricted finite W-algebra. So this tiny little algebra, which is the fundamental unit of currency in describing reps of G, is suddenly now given a presentation by this interesting Yangian. So there is lots more work to come on this. There are a few papers in production, and that's all. Thank you for listening. So sorry about the early start. I'm in Kyoto, so arigato.
Thank you very much for a very interesting talk. I have one question about the characteristic of the field to be not too small.
Yeah.
What does it mean? For example, for p equal to 2, you give some examples, but what about 3 or 5?
So the exclusions, basically, if you have a root system, then you can write the longest root as a sum of simple roots, and they will have certain integer coefficients. And what you want is for the prime characteristic not to divide those numbers. So what would happen if you did have a prime dividing that number is suddenly two root spaces would coincide, and you would no longer have your Lie algebra being diagonalized into one-dimensional root spaces by your torus. And so we just have to exclude p equals to 2 for the classical types, p equal to 3 for all the exceptionals, and then p equals to 5 for type E8. For special linear, it's a little bit more complicated because we also want to assume that there's a non-degenerate trace form that I mentioned, and that happens if p does not divide n for epsilon. So there's the exclusion.
Thank you. More questions, comments, please? Either notions. Let's thank Luis once more. Thank you very much for very interesting.
Very much for inviting me. Thank you.
So then we close our seminar, our session. Thank everybody for joining our seminar.
Yeah.
See you next seminar.
Thank
Bye-bye.
you. See you then. Bye-bye.